What's up, guys? It's me again, Sir Ernest, and today we are going to talk about generalized momenta. Now, in order to understand generalized momenta, let's consider a free particle. Okay, so what is a free particle? A free particle is a particle that is free to move in a uniform potential energy field. So the potential energy generally of this free particle is a constant. So let's say that value is mu naught. And this mu naught can be 0. But more importantly is that this potential energy tells us that the derivative of your potential energy with respect to position, let's say in the x direction, is equal to 0. Okay? So what does it mean? It means that the net force acting on the object, or acting on a particle, is equal to 0. So, if you have a free particle whose mass is m, and let's say moving in one dimension, let's say in the x direction, so that means it has a velocity x dot. This tells us that the particle will be moving with a kinetic energy T equal to 1/2 mx dot squared, while the potential energy is equal to mu naught, and that is a constant. So that means the Lagrangian of the system L will be equal to T minus U, or 1/2 m x dot squared minus mu naught. So you will notice here that our Lagrangian is only a function of velocity, x dot. Therefore, the equation of motion of this particle can now be rewritten as the derivative of L with respect to x minus total derivative with respect to time of the partial derivative of L with respect to x dot, and this is equal to 0. So we already know that the Lagrangian is only an explicit function of the velocity. Therefore, the partial derivative of the Lagrangian with respect to position is 0. Okay? And this derivative is actually equal to the derivative of your kinetic energy with respect to velocity. And this is equal to 0. And what is this? This is actually equal to m x dot from here, where the partial derivative of t with respect to x dot is m x dot. And the derivative of this with respect to time is 0. And what does it mean? It means that this quantity is a constant. And you will also notice that this quantity is actually your Newtonian linear momentum, which is a constant. Amazing, right? So from knowing the Lagrangian and knowing that the Lagrangian is given by this, we found out that the linear momentum of a free particle is a constant, and this is your conservation of linear momentum. Now, we could extend this to several coordinates, or any coordinates that you want. But the point is that if the Lagrangian is independent of a coordinate. So you'll notice that L is only a function of your velocity. Okay, where Q K dot is your generalized velocity. So this is where K is equal to 1, 2, 3, up to any number n, which is your degrees of freedom. So this tells us that a solution to the equation of motion, the Euler-Lagrange equation, leads to a constancy of a quantity that can be identified with the momentum of the system, referred to the missing coordinate. So in our illustration earlier, the missing coordinate in the Lagrangian is x. So the associated momentum along that coordinate, which is our linear momentum, would be constant. Okay, so we call this our momentum P equals m x dot. So this is your linear momentum. So from here, we take note our formal definition of what we call the momentum of your free particle, wherein the momentum of your free particle px dot, p sub x, is equal to m x dot, and this is equal to the partial derivative of L with respect to x dot. Okay, so for a system of described by generalized coordinates. Okay, so for a system of general coordinates q, let's say q1, q2, let's say up to qn, the quantities pk is equal to the partial derivative of the Lagrangian with respect to the generalized velocity. We call this the generalized momenta. So we say it's momenta, so that pertains to all possible momentum quantities that is related to your, or that is associated to each of the generalized coordinate that you choose. Okay. So, going back to our equation of motion, okay. So again, the Euler-Lagrange equation which is written in terms of generalized coordinates and generalized velocity is derivative with respect to time of the partial derivative of L with respect to q k dot, and this is equal to partial derivative of L with respect to qk. So because we already found out that this quantity is your generalized momentum, so that means, okay, the Euler-Lagrange equation can be rewritten in terms of the generalized momenta as p k dot, and that's equal to partial derivative of L with respect to qk. Okay, so therefore, when the Lagrangian, as I mentioned earlier, is not an explicit function of qk dot, okay, that means the time derivative of your particle, time derivative of the momentum of generalized momentum of your particle is equal to 0. Okay, and then this leads us to the generalized momenta at that specific coordinate to be constant. Okay, so in other words, when the missing coordinate is ignorable, its conjugate momentum is a constant of motion. And this definition enables us to discover the corresponding momentum of a system outside the usual linear and angular momentum that we'd already known during our general physics classes. Also, this is very consistent to our discussion then. Remember that during our discussion in Newtonian mechanics, that when the particle experiences zero net force, okay, so we know that the net force from Newton's law is the derivative of the momentum of your system with respect to time. Now, if the net force acting on the particle is zero, that means the time derivative of your momentum is zero, which tells us that momentum is conserved. Specifically in this case, the linear momentum is conserved. Okay, so Newton's law is very much consistent to our Euler Lagrange equation or your Lagrangian dynamics. Okay, so this ends our discussion on generalized momentum, and we're going to use this in our discussion involving conservation of energy, wherein we're going to introduce there the concept of the Hamiltonian of a system. So in the meantime, I hope you learned something today, and thank you for watching. I'll see you again in the next video. Bye-bye.